Okay, once again we are in the Colour Academy, session number 4, sort of an introduction to LAB and ICC profiling, or the practical application of in digital printing. Again, I'm trying to start these sessions off with the same intro, which is that although we have a lot of experts working for us, a lot of people experienced in graphic arts, we also have a community of engineers who don't have that expertise, don't come from those environments. And the sets of educational training type videos we're doing here are to ease you into that world and give you something to think about. We're trying to keep it low science, high practical, and but if there's any ever deeper questions to ask, you can always ask those. So let's get started today. I'm going to try to look at an introduction to LAB colour and look at an ICC workflow. We're going to address the idea of source profiles and printer profiles and device links. Look at something called A to B tables and B to A's, so you have an understanding that not all profiles are built the same. And we're going to have a quick discussion on delta E and what does that mean. The ICC world is a very, very big world. Over 20 odd years, if not longer, been in development. It has a grounding in quantum physics with some very difficult ideas around colour, and is also formulaic and eventually becomes a program. However, we're going to look at the tip of the iceberg, and we're going to look at in an ascending scale what we need to sort of understand at a practical level, either in the field or to have a conversation with a customer who also is unsure about this kind of technology. So we're going to discuss mindset first. Changing mindset's needed often. So we have, again, if you are an expert, then there's some of these ideas and concepts will seem very easy to you, but you've got to remember that we have to communicate this to printers and printing companies who may not understand these ideas. I'm going to look at source profiles or emulation profiles, printer profiles, talk about delta E, and we will cover editing profiles, not in this session, but it's something that you will need to eventually understand. So one of the hardest conversations to have is with the printing company or printer or operator themselves when discussing colour management and colour control on a digital press. They will usually have expert knowledge in their traditional printing process, and so they'll have a certain way of thinking about the way colour is put together and what controls colour and the like. And if you've ever tried to explain to a printer that really pulling TCR curves around like you might do for a CTP system is not a really good idea in a digital press, because they're very difficult to reproduce. It can be a tricky conversation. So we somehow have to break the inertia and discuss how we have to move away from this standard way of thinking. So we have to understand ourselves at a certain level what we mean by colour. To our maybe to yourselves or certainly to the printer, colour is something which happens with CMYK and happens with their inks. But when we talk about colour and colour management, we want to start to move away from this idea of how it's made, but more to what would you like to see. And what we see today, when we see colour, we see a visual spectrum. Our eyes have a perception of the natural world, and our brains convert that into colour. And to mimic the natural world, we also now have spectrophotometers, not to be confused with densitometers. Might sound a silly thing for those of you with some knowledge, but often in the print shop, this is completely new. And a spectrophotometer, just like our eye, is able to detect individual colour. So not how it's made, but the actual colour that we would see. And that's called a spectral response, and that's illustrated with the little graph there. And for every single colour, there is a different spectral response. So in this way, we can start to lead ourselves down a road of thinking logically that we can start to maybe model colour if we can start to describe it in a finite manner. Well, we end up, or we've ended up, should I say, there's been other models in between, but as human beings, we like to model the natural world so we can communicate it. We talk about abstract things such as time, length, weight, mass, but we model those in terms of things we can understand and communicate with one another. Hours and minutes, for example, with something like time. And we use this LAB. L is for luminance, and we see there the B axis is yellow and blue, and the A axis is green and red. And that's illustrated in the 3D diagram we see there. And I'll be surprised if many of you haven't seen this diagram before. But so spectral responses are response to real light or real colour, and we change those responses into an LAB model because then colours have a natural relationship to one another. So it's a model is LAB, but if you want to think about it in a very more simplistic way, a LAB value is a finite value of colour. And although for those of you who know a little bit more about this subject, you'll know that's not 100% true, but it's a big enough leap, believe me, for most printers to start to get them to think about this in this manner. You know, we are asking them to change their mindset. So, colour communication, this is a slide from an earlier presentation. Let's just recycle it here. Is if we describe colour as 100 and 100, process red, but print it on a high grade and low grade paper, we know we see something different. So that leads us straight away to a conclusion that we can't communicate what we would like to see in terms of CMYK. And using LAB as a communication method helps remove that ambiguity. So there's no right or wrong, but if I'd like to see this kind of red, then this is the LAB I would like to communicate. However, if I would like to see this kind of red, this is the LAB I would like to communicate. So it's just a way of defining a measurement. And to just hammer this home, again using this idea of a unique measurement and human concepts of communication. If I ask for a metre of wood from 3 factories, I don't need to give them a sample of what that metre is. Likewise, if I request from a printing company an LAB value, if they understand colour management, they should, within a tolerance, and we're going to discuss these tolerances in a bit, produce on different machines, different technologies, as near as possible that request. So we can understand maybe that an individual colour has a finite value, but, and again robbing this slide from an earlier presentation, but it's again felt appropriate to keep it in. How do we actually capture the whole printing process? So if we can imagine we can capture the single colour, then it's not much more imagination to think we can catch a whole bunch of colours. And in fact, if we do enough patches, we can capture the colour characteristics of a whole process. And this is what we would call a reference profile. So I'm just making sure my slides are in the right order. Yep. Okay. So we have 2 types of profiles in a digital workflow. We have what we would call a printer profile, and this contains the characteristics or the colour potential of a digital device. So for example, our Xicon here, and if we were to use the Xicon colour control solution, we would print a target, measure that target, upload that target, and receive a output profile back. And a source profile or an input profile, such as the industry standards we find out there in the world, like FOGRA and GRACOL, are are made by averaging a lot of data from printing processes working to standard printing procedures, and the results are these industry standards which capture the look and feel, or an agreed look and feel, should I say, offset in the case of ISO, and they exist because they're achievable, and we can all decide on. We can all agree that they make a good job. So what is a source profile? We get mixed up because there's lots and lots of similar terminology used. So a source profile or emulation profile or input profile are all the same. For me, these describe what we would like to see eventually on the paper or on the monitor. And again, these are either industry standards or you can make your own, but let's just stick to industry standards for now. And we have, they are a translation from INC or CMYK to LAB. And a output profile essentially is describes our printer and describes our LAB to CMYK. So we can think of how they're used in a RIP, similar to this. We have two independent files. One describes what I would like to see. And so as our data comes through the system, pixel by pixel, the CMYK values in that data are tagged or translated to an LAB value. So this is the colour I'd like to see. And then our printer profile has those colour values available, and then has a translation table giving a separation value on that printing process which will allow that to happen. And we think of this as a to B table. So we have A to B is ink to light or separations to light, and a B to A table is a light to separations. So we can see here I don't think we can zoom in. We have the same LAB value, but we have different CMYK values to make that happen on the output. So this concept of source and output profile is 100% key to a digital controlled digital output. Okay. Here we've got 4 examples of major digital RIPs which are out there in the world, and although the GUIs are slightly different, we'll see that they all have the same kind of layout. All of them are asking what our source profile is, then all of them are asking what our output profile is. And remember, our output profile is unique, we make that, and our source profile is the aim or goal of the printer in terms of colour. So again, another simplified diagram of what's going on in the X800. We have our source profile, i.e. what would you like to see. We have our printer profile, which is linked to our calibration, and those two are the vehicle or the mechanics that allow that to happen. And the important thing to remember here now is we have a goal and an aim, and that goal and aim is static, and we can forever keep updating our printer or updating our calibration to make sure that goal is maintained. So we're not lost in what we're hoping to reproduce. So we're going to have a discussion on device links. You may have heard of these profiles in the past. So classically, we have our situation here where we have two individual files dictating the colour output, and they're joined in this conversion space. Now, if the same file moves through this RIP 100 times, it's the same conversion happening every single time. So the idea with a device link is that you can cut the middleman out and go straight from CMYK to CMYK. So it's a single file, it's pre-calculated. There are pluses and minuses to both of these ways of working. Device links are much more editable, slightly more difficult to handle in the RIP, especially from a customer's input point of view, and also have an impact on speed of ripping as well, because this pre-calculation help files move through the ripping and colour management process much faster. So standard workflow is we have our output profile or source profile, and then we have our unique printer profile, or we glue those together and we create a device link. So we're going to discuss now rendering intents. Something you'll see in the RIP are rendering intents, and I'm sure it's something we've all heard about, but what actually are they? Well, we have colorimetric and absolute colorimetric, and we'll start with colorimetric. So if we take a view to the small gamut diagram we have over here, we have two processes which are very similar, but as you can see, the green process, which is actually a Zycon, is slightly smaller than the red process, which is ISO. Within relative colorimetrics, the colours which can be achieved are accurately maintained. So if we look at the moving diagram, the colours which are inside the circle don't move. They are as accurately as possible rendered. And colours outside of the gamut are moved to the nearest possible position inside the gamut. Now, as long as your colours are only slightly out of specs, this is a very good way of printing and gives a very accurate result. Now, absolute colorimetrics, when we take our when we make our input profiles, or we take our industry standards, inside of those we have the Paperwhite, and I've exaggerated it there with a yellow. And if we apply absolute colour metrics, again it's exaggerated on screen, that paper white is applied to the output profile. It's not desirable often. Sometimes proofers work this way, and you'll see a background on the proofing substrate. However, interestingly enough, both the Gracol Ideal Alliance and the FOGRA specifications for digital printing today insist on absolute rendering as the printing methodology. Now you can turn off the paper white on some profiles, but maintain the white, the cast of that throughout the other colours. There's arguments for and against both of those, but for those of you curious what these are when we see them in the RIP, I think this describes it very nicely. Next we have perceptual. So the idea with perceptual is only really comes into play where you have a much bigger space and you want to move the colours into a smaller space. So ideal for RGB printing, but also ideal when you've got a printing process which has a very, very small gamut, let's say newspaper, and we want to make the most and make the best kind of images possible on that kind of substrate. So it's not necessarily RGB to CMYK, it can be a CMYK to CMYK situation. It's not so accurate, as you can see. As the other colours move in, it shuffles the other colours to accommodate them. And what you'll end up with is a smoother image with all details still maintained, but the colours of those details will have been moved. There is saturation, but I've never, in all my years, never used saturation as a rendering intent, so decided to leave it out of this presentation. So, moving on. Delta E. So the E, and I'm not even going to try to pronounce this word, actually stands for sensation, and as we know from mathematics, delta means deviation or difference. But again, this is something somebody in a print shop with no mathematical background may not understand or may not take for a simple way of thinking about it. So we know we have our three-dimensional space, we discussed that earlier on, LAB, and a colour is defined as an LAB coordinate. So first of all, delta, if we have one coordinate and another coordinate, the difference between those coordinates is delta E. So the first practical use of this idea is it's just the difference between two colours to compare them. Now that might be two colours which are totally different colours, or you want to compare two colours that are supposed to be the same or similar. What does it mean? I hate having to this discussion with most people, but between 0 and 1, it's almost an invisible difference. Between 1 and 2, a very, very small difference, and only really obvious to a trained eye up close and looking for something. 2 to 3 to 4, the difference can become obvious, but again, you need to be looking for it. And then above 5, it becomes an obvious difference, and 6, 8, a very obvious difference. Note that and I just put this note down at the bottom. 5 is accepted as the difference in primaries within the Fogler standard. Just out of curiosity. So it can be set, the second use of it is it can be set as a benchmark of difference. It can also be used as a zone, a tolerance zone. So the idea is if our colours fall inside that zone, they're going to pass, and if you fall outside that zone, you fail. But things do get a little bit more complicated. I don't know how well this is being translated onto your screen, but if this is our theoretical blue that we are trying our aim, then this blue looks pretty good to me, and this blue does too, and this is looking good, but this is greeny blue, and for me is still the wrong colour. However, because it's in the bubble of tolerance, we allow it to pass. So sometimes we can have a false negative, or a false positive, should I say, i.e. something passes, yet it visually looks wrong. Well, to help remove this, different formulas over the years have been used to calculate delta E. So the classical formula, delta E 76, is accurate to the human perception of about 75%. So that means 25% of the colours fall into our example of the little blue, greeny blue dot, not looking quite right. Then we have delta E 2000 becoming more and more acceptable, and it's a much, much more natural fit to what we would reject or pass in terms of viewing colour. And it's said to have around an accuracy value of 95, so only 5% will still fall into that area. And delta E 2000 works on the idea of an ellipse as opposed to a sphere, and that ellipse has a bias to the correct visual perception. So benefits of using a colour managed workflow as opposed to a non-colour managed workflow. We have an aim. We have something we are trying to achieve. If we go for industry standards, those aims are globally respected in terms of colour. Now, even if our gamut is sometimes smaller, It still might mean that we produce 99% of that aim. And we've seen through the effect of the rendering intent how we can bring those colours in. Once you have a colour managed workflow, be it perceptual or relative, and you've agreed with your customer on this is the output that you will make, you can keep on top of the output by simply creating either new output profiles or simply calibrating and keeping the press in good shape over time. So you're always moving back to the same aim, rather than producing something where you don't know what all you know is a density value and a linearization, but you don't know the colour, what was achieved. So this allows you to have consistency through different engines and media, and I think this is the main reason to move away from a non-colour managed workflow. So a shorter one today than most. If you want to unmute and ask any questions, feel free. Otherwise, I will say adieu for now. Any questions?